Good morning. Hope everybody had a good weekend. We are going to pick up where we left off last week. This is still section 2.5. So we've got a few more examples to finish up here. Hopefully get into 2.6 today also. So that's kind of my goal. Then that only leaves us with section 2.8 for this unit, which we should be able to cover between tomorrow and Wednesday for sure. Some of those examples take a little longer, so it might take us a couple days. But the plan is still to finish up this unit by the end of this week, even with review. I'm thinking we'll probably finish up on Wednesday. That means the test will be posted Wednesday night at midnight, and then due Friday by midnight. Okay, so that's the plan for right now. Don't forget that the next homework, which covers 2.4 through 2.6, is scheduled to be due tomorrow night. Again, we should be able to hopefully get through 2.6 or at least get into 2.6 today. So you should have everything you need to complete that homework by the end of today, but it will be due by midnight tomorrow night. And then the only other homework for this unit is specifically section 2.8. Again, some of those problems take a little while longer, but that'll be due towards the end of this week also along with the test. Okay. Any questions, comments, concerns before we get started today? All right, so let's take a look here at example 4. Again, this is still section 2.5. So we want to find the first derivative, f prime of x, if our function here is 1 over the cubed root of x squared plus x plus 1. Right, so what's the first thing we might want to do with this function if we're looking for our first derivative here? Okay, so we could go that route, right? We could say, well, let's do this as a quotient since we have a fraction here. Is there a way that we could actually rewrite this one, though, so that we don't have to deal with quotient rule? Okay, good. So we could change this first off to f of x is just 1 over x squared plus x plus 1 to the 1/3 power, right? So that cube root there, we can change it to a fractional exponent, so it becomes a 1/3. Now what could we do with it? Okay, so if we bring it up, what's going to happen to the 1/3 then? Becomes negative. Perfect. So I'm going to rewrite this now as just f of x equals x squared plus x plus 1 to the negative 1/3 power. So by doing that, now we've eliminated the need to use quotient rule, right? So now we can just think of it this way. Now, what rule are we going to have to use on this one, though? Okay, so it's a power rule, but within that power rule, we're going to have to remember to do what? Okay, so it is going to be the negative 1/3 out front, right? Because that's part of our power rule. But what other rule do we have to incorporate this time? Think back to the examples we did towards the end of last week. What's that rule called that we're going to have to use here? It's a chain, right? So in this case, we have an inside function and we have that outside function, which is the negative 1/3 power. So we're going to use a power rule, but within that's going to be a chain. So what could we let our u value be equal to this time? Good. Everything inside the parentheses, so x squared plus x plus 1 is our u value, which means now I can rewrite my function as just u to the negative 1/3 power. Now, when I go to take my derivative then, what's the derivative going to look like for this one? Perfect, right? So we bring down the negative 1/3, we keep our u, and if we subtract 1, we're subtracting 3/3 from that. That's going to give us a negative 4/3. Now, because it's a chain rule, what else do we have to remember here? Multiply by u prime, right? So the derivative of u, which means I need to come over here now. What's our u prime value going to be? Good. So just 2x plus 1 using our power rule over there. So now we have everything we need. We substitute back in. So we have f prime of x. It's going to be negative 1/3 times x squared plus x plus 1 to the negative 4/3 power times u prime, which is just 2x plus 1. Okay, now, before I clean that up, any questions about how I got to that point there? All right, so now at this point, we just want to get rid of the negative exponent. That's the main thing here. We have f prime of x. The 2x plus 1 here is going to go in the numerator along with the negative 1. So we'll have a negative 2x plus 1. The 3 is already in the denominator, so I'll keep that down here. And then everything in parentheses here to the negative 4/3 gets moved to the denominator to become a positive exponent. And so we get something that looks like this now. Any questions on that one now? All right, so again, just keep in mind, if you have fractions like this, but you don't have any x's in the numerator, most of the time it's going to be to your benefit to rewrite it first so that you can use a power rule instead of having to use quotient rule, okay? All right, so let's take a look at this one now. So we have g of t equals t minus 2 over 2t plus 1, all raised to the 9th power. All right, now this time, there's not really anything we can do to simplify this one. So what are we going to have to do to find the derivative? Okay, so we are going to need f and g this time because there's going to be a quotient rule within this. But overall, this is actually going to be what rule? So since we have that fraction raised to the 9th power, it's going to be a chain, right? So we have an inside function here with an outside function. So it is going to be a chain rule. And within that chain rule, there's going to be a quotient. So what I'm going to do first, let's identify the u value so that we can rewrite it in terms of u. And then we'll look for the derivative of u. So what are we going to let our u value be this time? Good. Everything in the parentheses, that entire fraction. So u equals t minus 2 over 2t plus 1. So now I can rewrite this as just u to the 9th power. Well, what's the derivative of this going to be in terms of u then? Good. So we need our 9u to the 8th power. That's just using our power rule. And then because it's a chain rule, we have to remember to multiply by u prime. So now we've got to go find the derivative of u, right? Leave myself some space here. To find u prime, what are we going to do first? Good. We need our f and our g function because it is a quotient rule. So remember, f is always the numerator. That's going to give us t minus 2. T is always our denominator. It's going to be 2t plus 1. So what is f prime going to be for this one then? Good, just 1. And g prime is going to be 2. Perfect. Okay. So now if we use our quotient rule, remember, start with g. So it's g f prime minus f g prime all over g squared. So if we start with our g function this time, we're going to have 2t plus 1. We're going to multiply that by f prime, which is just 1. Then we're subtracting our f function, t minus 2, times g prime, which is 2, all over g squared, 2t plus 1, all squared. All right, now we just need to clean up what we have here in the numerator. So 2t plus 1 times 1 is just 2t plus 1. Then we can distribute the negative and the 2 here, so it's going to give us a minus 2t and a plus 4. Keep your denominator factored, 2t plus 1 squared. And so then if we combine like terms in our numerator, what's going to be left there? Just 5, right? The 2 t's cancel out. So we get 5 over 2t plus 1 all squared. So there's our u prime value. Now we know u prime. Now we can substitute everything back in over here. So g prime of t is going to be 9 times t minus 2 over 2t plus 1, all to the 8th power. And then we're going to multiply that by u prime, which is 5 over 2t plus 1 squared. All right, now, at that point, we could put all these fractions together just to clean this up a little bit more. So let's think about what we've actually got here. What's going to be in our numerator? So let's just start with the numbers here. We have a 9 and we have a 5. We can multiply those together. So what's that going to give us? 45, right? So we're definitely going to have a 45 here. And now the t minus 2 is in the numerator, but it's technically being raised to what power? The 8th, right? So this is just going to be t minus 2 to the 8th power. Now let's look at the denominator. We have a 2t plus 1 here in the first set of parentheses, but then we have another set of 2t plus 1s raised to the 2nd power. So how many 2t plus 1s do we have altogether in the denominator now? So there's more than 3, because how many do we actually have in that first set? There's 8 in the first set, right? Because that 8 would be distributed to both the numerator and the denominator. So how many overall do we have then in our denominator? 10. So this is actually going to be 2t plus 1, all to the 10th power in the denominator now. And that's where I would stop, right? I wouldn't expand any of that. There's nothing else we can do to simplify it. So leave it just like that now. Any questions on that one? All right. Take a look here then. So now we want to find the derivative. We've got 2x plus 1 to the 5th times x cubed minus x plus 1 to the 4th. All right, so how are we going to do this one? So what rule or rules are going to be involved this time? Start there. Okay, perfect, right? So it's a product rule first and foremost, right? Because we have this 2x plus 1 to the 5th, and we're multiplying it by x cubed minus x plus 1 to the 4th. But then to find the derivatives of each of those pieces, we're going to have to use chain rule, right? So first step, let's go ahead and identify f and g. So again, I'm going to let f be 2x plus 1 to the 5th. And I'm going to let g be x cubed minus x plus 1 to the 4th. And that way, I know this is just going to be a product rule overall. So when I go to find my derivative, It's just going to be f times g prime plus g times f prime. So now I just need to find the derivatives of each of those. And this is where the chain rule is going to come in, right? Because to find the derivative of each one of these, we're going to have to use a chain rule. How am I going to find the derivative of f then? Okay, so what's your u value then to find the derivative? Okay, good. So we'll let u be 2x plus 1 here, which means our u prime value is going to be what? 2. Good. So now I'm just going to rewrite my f function as u to the 5th, which means our f prime is going to be what? So just in terms of u here, what would the derivative be? Okay, so that's the overall. That works. Okay, so let me do it in terms of u, and then I'll substitute everything in because that's what you're going to get. So it's going to be 5u to the 4th times our u prime. And then if we substitute the u value and u prime in there, that's going to give us 5 times 2x plus 1 to the 4th power times 2. Okay, slide this down just so I can fill in the last step. So now if we multiply here, the 5 and the 2, we can actually multiply together on the outside. So that's just going to give us 10 times 2x plus 1 to the 4th power. Any questions about how I got that derivative? Okay, so then if we go over to the g function, what's our inside going to be this time? Good, so everything in the parentheses. I'm going to call it v. We've already used u1 here, so I'll just call this one v, x cubed minus x plus 1. So what's our derivative of that going to give us? Good, 3x squared minus 1. So now when we come up here, rewrite this in terms of u, that's going to be u to the 4th power, which means our derivative is going to be 4u to the 3rd times u prime. And now when we substitute, we're going to get 4 times x cubed minus x plus 1 to the 3rd times 3x squared minus 1. And in this case, I would probably keep it like that. If you wanted to, you could technically distribute the 4 to the 3x squared minus 1, but really keeping it factored out that way is fine too. All right, so now we have all the pieces, right? We have our f and f prime, we have our g and g prime. We know this is going to be a product rule overall, so now we can just substitute everything in over here. I'm actually going to do it way down here because it's going to be a long line. So start with f. It's going to be 2x plus 1 to the 5th. Multiply that by your g prime that we just got there. So that's 4 times x cubed minus x plus 1 to the 3rd times 3x squared minus 1 plus, and then we're taking our g function, x cubed minus x plus 1 to the fourth. And we're multiplying that by f prime, which was 10 times 2x plus 1 to the fourth. Okay. Now, honestly, the only thing you might want to do here is pull out those numbers so they're at the front of each of your terms. Other than that, there are some common factors too if you wanted to bring those out, but that's not really a necessary step. So I would probably write this as 4 times 2x plus 1 to the fifth times x cubed minus x plus 1 to the third times 3x squared minus 1 plus, and then just bring the 10 to the front of this one. So 10 times x cubed minus x plus 1 to the fourth times 2x plus 1 to the fourth. And again, if for some reason you needed to set this equal to 0 and solve for x or something like that, then you would look for common factors. So there's like a 2x plus 1 here and a 2x plus 1 here. So you could bring out 2x plus 1 to the fourth. We also have the x cubed minus x plus 1 in common here. There's 3 of those, so you could bring out 3 of those and then just keep whatever's left over in parentheses there. But again, for my purposes here, that derivative is perfectly fine. It's only if you needed to solve for something that you would want to do the factors here. Any questions on that one? So what you're seeing here is about as involved as your derivatives are going to get, just because, in this case, we're doing a combination of product and chain rule, right? The other one we had quotient and chain rule combined. We're going to look at some chain rule within a chain rule in these last few examples here in this section, but that's really as far as it's going to go, right? So as long as you can do like 2 or 3 steps kind of all combined within the same derivative, that's about all you need to worry about. I would never give you anything where there's like 4 or 5 different functions all combined. All right, so now we want to find f prime of x if f of x is sine of cosine of tangent. Okay, so notice this is not multiplication. This is actually the sine of the cosine of the tangent of x. All right, so what rule are we going to have to use here to find this derivative? Okay, so think about what's going on here. There's no products, there's no quotients, right? Sine of a cosine of a tangent. So it is a chain rule, right? Now, if we use chain rule here, what would you let the inside function be? Good. So we've got to keep the entire cosine of tangent of x here as our u. We're going to say u equals cosine of the tangent of x. So now I can come back over here and say, well, that means my f of x in terms of u is just sine of u. Now, to be able to find, let's think about this. What would f prime of x be in terms of u now? Cosine u, derivative of sine is just cosine, but because it's a chain rule, we have to remember what else? Times the u prime. Good. Which means I need to come over here then and figure out what u prime is going to be equal to. How are we going to find u prime? It's another chain rule, right? Because now we still have cosine of the tangent of x. So we're going to have to use a chain rule just to find that derivative. What's our inside function going to be this time? Tangent, good. So again, I'm going to use a different variable. We'll go with v this time. And that'll be our tangent x. Which means I can rewrite my u as just cosine of v. And so now what is u prime going to be equal to in terms of v? Negative sine of v, good. But because it's a chain rule, we have to remember to multiply by the derivative, right? So we're going to multiply this by v prime this time. So now we just need to know the derivative of v. Well, what is the derivative of tangent x? Secant squared, good. So this is going to give us secant squared x as our derivative there. Now we should have all the pieces we need. We just kind of have to work backwards and substitute things in. I'm going to find my u prime first. I'm going to take the v value and substitute it in. So we'll get negative sine of tangent x times v prime, which is secant squared x. And at that point, we have our u and our u prime, and we can substitute those back into the f prime of x over here. So f prime of x is going to be the cosine of the u value, which is cosine of tangent x. And then we're going to multiply that by u prime, which is all this stuff here, negative sine of the tangent x times secant squared x. And honestly, the only thing you might want to do is bring that negative to the front so it's not just sitting in the middle of that product, but all of this is just being multiplied together. There is nothing that you can combine here. So this is just negative cosine of the cosine of the tangent of x, sine of the tangent of x, secant squared x. And again, just be careful with your parentheses here. Recognize what's a composition of functions and what's a product. So a lot of times people want to say, oh, well, cosine, that's cosine squared. No, because this is the cosine of the cosine, not a product of two cosines. And then same thing, we can't combine this sine tangent x with cosine tangent x because that cosine tangent x is inside of another cosine function. Okay, so there's nothing else you can do to multiply any of that together. That is as simplified as that's going to get. Again, this is an example of a chain rule within a chain rule because we have the cosine tangent as one inside function and then the tangent inside that function. Any questions there? All right. So now we want to find the derivative of square root of secant x cubed. So what do you think our first step is going to be this time? Okay, good. So let's change this and just rewrite the function as secant x cubed all raised to the 1/2 power. So anytime you see a radical, that's going to be your best bet, right? Because then we can just use power rule to find that derivative. Okay. Now what are we going to have to use to find this derivative? It's a chain rule, right? So what are you going to let u be equal to this time? Good. So secant x cubed is the inside, so u equals secant x cubed. So now I can rewrite my original function as just u to the 1/2 power, which means that y prime is going to be equal to what in terms of u? Good. 1/2 u to the negative 1/2. And because it's a chain rule, what else do we have to remember? Times the u prime. Okay. So now we need to find u prime. How are we going to find u prime? So what rule are we going to have to use here to find the derivative of u? It's another chain rule, right? Because we're taking the secant of x cubed, where x cubed is the inside function. I'm going to have to bring that out again. So again, I'll call that v. Let that be equal to x cubed, which means our u is actually just secant of v. Well, what is the derivative of secant v? Good. This is the secant tangent one, right? So this is going to be secant v, tangent v. But again, it's a chain rule, so just don't forget, we also need to multiply that by v prime now. Well, what is v prime going to be equal to this time? 3x squared. Good. All right, now we've got everything we need. It's just a matter of being very careful as you substitute back in. So our u prime over here now, if I substitute the v and the v prime, we'll get secant of x cubed, tangent of x cubed, and then times 3x squared. Now we have our u and our u prime all in terms of x. We can substitute that over here to our y prime. So we have 1/2. U is secant x cubed raised to the negative 1/2 power. And we're going to multiply that by the u prime, which is all of this stuff. Secant x cubed, tangent x cubed times 3x squared. All right, and then as always, if you have negative exponents, we want to get rid of those, right? So I can move that to my denominator. Everything else here is actually going to stay in the numerator except for the 2 that's already in the denominator. So when I do that, we'll just have 3x squared secant x cubed tangent x cubed all over, keep the 2 down here, and then bring the secant x cubed to the negative 1/2 down. So that's secant x cubed to the positive 1/2. And in this case, the only other thing you could do, if you wanted to combine those secant x cubes, you could, and just have a secant x cubed to the 1/2 in the numerator and cancel out the 1 in the denominator. Not necessary, but if you wanted to combine them, it is a possibility since everything's just multiplication and division here. Any questions on that one? Okay. And like I said, that's about as complex as they're going to get, just because in this case we have a chain rule within a chain rule. We're dealing with trig functions and power functions. So just keeping everything lined up, right? Showing those steps is definitely your best friend in this case, right? So just think about what pieces you need, and then just kind of keep going from there until you get everything you need in terms of x, and then just back substitute back to where we started, okay? All right, so that's all we've got for that section. So that was 2.5. So we're going to move on to 2.6 now. All right, so 2.6, this is what we call implicit differentiation. So what we're going to look at now is, what if you have a function, or maybe even just an equation that's not a function, and you want to know its derivative? Okay, so in this case, we're going to have equations where maybe there's x's and y's on both sides. It's not easy to solve for y. How do we actually find the derivative of y in those cases? Okay, so with implicit differentiation, we don't actually need to solve the equation for y in terms of x to find the derivative. Instead, we can actually use implicit differentiation, differentiate both sides, and then solve for y prime. So you're going to see when we take these derivatives, what we have to remember, because it's technically going to be like a chain rule as we go through each of these, and then we just have to get y prime by itself once we've taken the derivative of both sides. All right, so let's take a look at this first one. We've got x squared plus y squared equals 25. We're asked to find dy dx. All right, now, first things first, let's think about what this equation is, right? So if we have x squared plus y squared equals 25, what would the graph of that look like? It's a circle, right? Okay, so this is the equation of a circle. Notice here, solving for y wouldn't be terribly difficult, but what's going to happen is when we take the square root, we're going to get a plus or minus. So you're actually going to have, the top half of your circle is the positive, bottom half of your circle is the negative. It's not a function, right, because it doesn't pass the vertical line test, which is why you need two different pieces. And that's why the derivative will be a lot more complicated to find if we solve for y first. Okay, so this is a case where implicit differentiation makes a lot of sense to try to find our dy dx. Well, to do that, all I'm going to do is I'm going to go step by step, term by term, left-hand and right-hand side, and find these individual derivatives. So if we look at our first term here, we're finding the derivative of x squared with respect to x. Okay, so notice here, we're doing it with respect to x. That's what that denominator piece tells us. What's the derivative of x squared with respect to x here? Two x, right? Okay, so that's just a normal derivative. We're going to get 2x. Then we have our plus. Now we want to take the derivative of y squared with respect to x. What do you think the derivative of y squared would be? Okay, 2y I agree with, right? So we just use our power rule like we always would. So it's going to be 2y. But because we're taking the derivative with respect to x, we have to think of this almost like a chain rule where u is equal to y, and this is really u squared. Okay, so just kind of stay with me here. This is going to give us 2u times u prime. Well, the derivative of u now, if I'm taking the derivative of y, but I'm taking it with respect to x, is going to be dy dx. So not only do we need a 2y here, we also need the dy dx. So that's why this is going to become 2y dy dx. Now you might be saying, well, why don't we need that on the x squared? Well, if we do a u substitution on the x squared, we would say, call it v this time. So we would let that be v squared, which would be 2v v prime. But now, if I'm taking the derivative of x with respect to x, this is just going to be 2 times x dx dx. Well, what's dx dx equal to? One, right? And so this just becomes 2x times 1, which is just 2x. That's why we don't need anything additional for the x terms. So if it's an x term, just take your derivative as you always would. If it's a y term, though, and you're taking the derivative with respect to x, we have to remember this dy dx piece now. Okay? So that's the only difference with implicit. We have to make sure we have the dy dx if we're taking the derivative of a y term with respect to x. Now, on the other side, 25, what's the derivative of 25? 0, right? Derivative of constant, always going to give us 0. All right, so now we've got everything we need. Now we just need to solve for dy dx. So what can we do first to get dy dx by itself? Go ahead and move the 2x over. So now we have 2y dy dx equals negative 2x. Then we would do what? Good. Divide by the 2y. So we have dy dx equals negative 2x over 2y. And in this case, if we simplify that, what would that give us? Just negative x over y, right? The 2's cancel out. So dy dx is just negative x over y. And that's our answer, right? So we were looking for dy dx, and we solved for dy dx here. Any questions about that one? So if it was asking for dx dy, then you would be taking the derivative of every term with respect to y instead. And so that first term would become 2x dx dy. And then the second term would just be 2y because that would be dy dy, and that would just become a 1. So yeah, so that denominator always tells you what variable you're taking the derivative with respect to. And so if you're taking it with respect to y, then the x gets a dx dy, and the y would just be a y. And this will come in later too when we're starting to take derivatives with respect to time. That's what we're actually going to be looking at in section 2.8. We'll have to remember a dt in our denominator because we're going to be taking derivatives with respect to time instead. Any other questions on that part? All right, now part B, we want to find an equation of the tangent circle at the point 3, 4. How does it look on a graph? So remember, if original equation is just a circle, right? The derivative here, negative x over y, is not really anything, right? It's just giving us an equation now to help us find the slopes of our tangent lines at specific points. And so that's what we're going to look at in part B, is to actually find an equation of a tangent line. But the derivative itself only gives us an equation to find those slopes. So you can't really graph that as is, right? Because it's just an equation in terms of x and y, where x and y are on the same side. Okay. But if I want to find the tangent line now at the point 3, 4, what can I do? Good, right? We know the derivative represents the slope of the tangent line. So if I'm looking for my slope, I can just plug in these values. I have an x value and I have a y value, and I have an equation here in terms of x and y. I'm just going to plug those in. That'll give us negative 3 over 4. So there's our slope. Now that we have the slope, how are we going to find the equation? point slope. Good. So remember, that's just going to be y minus the y1 value. In this case, that's 4, equals our slope, -3/4, times x minus our x1 value, which is 3 in this case. Again, that equation there is perfectly fine. If you want to distribute and get it in slope-intercept form, you can do that also. Okay, but that is the equation of our tangent line to our circle at the point 3,4. Now this we can look at on the graph to check and make sure that our answer makes sense. Okay, so let me switch over to Desmos. Let's take a look at what we've got. All right, so our original was x squared plus y squared equals 25. Let me refresh this just to get all the trig stuff off. X squared plus y squared equals 25. There's our circle, radius of 5. And then the equation that we got for our line, our tangent line, was y minus 4 equals -3/4 times x minus 3. There's your tangent line. It should go through the point 3,4. There's our point 3,4. That checks out. Again, the negative x over y piece by itself only gives us an equation now to find the slopes of tangent lines at any point. So graphing wise, right, it's not really pertinent to what we're looking at. It's only once you actually know a specific point you're trying to go through, then we can actually find the tangent line. Any questions on that one now? All right, let's go ahead and take our break. So I've got 10, let's say 11:03. We'll get started back up and we'll finish up this section. All right. So let's take a look here at example 2. So we want to find y prime, and this time our equation is x cubed plus y cubed equals 6xy. All right, so we're going to go through that same process here. We're just going to take the derivative on both sides because solving for y would be extremely difficult this time. So let's go term by term. What's our derivative for x cubed going to give us? Three x squared, right? So because we're taking derivative with respect to x right now, that's what y prime represents. Okay, we just get 3x squared. Now, what about the y cubed term? What is that derivative going to give us? Okay, so we get 3y squared. And then we need the derivative of y with respect to x, right? So just make sure it's dy dx instead of dx dy, or y prime is the same thing as saying dy dx. So we can actually just put y prime there instead. And this just makes it a little easier so you're not writing dy dx over and over again, right? And moving that from side to side. Okay, so I'm just going to call that y prime. Any questions on taking the derivatives on the left-hand side here? Okay, now let's look at the right-hand side. How are we going to find the derivative of 6xy? Okay, so think about what we've got here, right? If we've got 6xy, what operation is happening in this case? So what operation's in there if we've got 6xy? So if you had an actual x and y value and you plug them in there, what are you going to do with them? Multiply, right? So this is multiplication. Well, if you've got multiplication, what rule do we have to follow for finding our derivative? Product, right? So make sure you recognize this is actually a product on the right-hand side. So we're going to have to use product rule. So we've got to identify what's our F and what's our G. So what could we let F be on the right-hand side? Okay, 6x works. And then our G function then would be just what? Just Y. Good. So now we need F prime and G prime so we can use our product rule. Well, what is F prime going to be? 6, right? Derivative of 6x with respect to x is just 6. What about the derivative of y? Okay, it's going to be 1, but because we're taking the derivative of y with respect to x, what do we have to put there? A y prime, right? So this is just going to give us 1 y prime or just y prime. Any questions about that part? remember our product rule is just f g prime plus g f prime. So if we come back over here now, that's going to give us 6x times y prime plus y times 6. So that's the differentiation step, right? We've taken the derivative of everything we've got in that equation. Now what do we have to do? Good. Get y prime by itself, right? We're trying to solve for y prime. Well, notice here I've got two different terms that have a y prime in them. So my first step is going to be to try to get all the y prime terms together, move everything else to the other side. So I'm going to move my y primes to the left, all my other terms to the right. Well, that means I'm going to subtract 3x squared to get it to the other side. So I have 3y squared y prime equals 6xy prime plus 6y minus 3x squared. Now I'm going to take the y prime term from the right. I'm going to move it to the left. So now we've got 3y squared y prime minus 6xy prime equals 6y minus 3x squared. Now, if I'm trying to get y prime by itself, what do you think we would want to do next? Good, right? So we have a common factor of y prime now. We can bring that out. So we're going to have y prime times 3y squared minus 6x equals 6y minus 3x squared. And so now we can do what? Good. Divide by everything in the parentheses. So y prime is going to be 6y minus 3x squared all over 3y squared minus 6x. So that is y prime now. Now, if you wanted to, you could factor out a 3 numerator and denominator and cancel out the 3's just to simplify that a little bit. But honestly, leaving it like that's fine too. Any questions on using implicit to find that derivative now? All right. Now, part B, we want to find the tangent to the folium of Descartes. That's just that equation that's given. Okay, that's what we call that thing. So at the point 3, 3. So what are we going to do to find our tangent line now? Good, right? So we've got points, right? We can plug those in to find our slope. So this time it's going to be m equals, we have our x value, we have our y value. So we get 6 times 3 minus 3 times 3 squared all over 3 times 3 squared minus 6 times 3. So if you simplify all of that, what should that give us for our slope? It's going to be -1, right? So notice here, basically all the values are the same on top and bottom, except the top's going to give us a negative, the bottom's going to give us a positive. And so this is just going to give us -1. Now that we know our slope, then we can do what? Point slope formula. So we have y minus 3 equals -1 times x minus 3. That is our equation, and we are done with part B. Any questions on that? Okay. Now, before I go into part C, let's actually take a look at this graph, right? Just to kind of check and make sure that what we got there makes sense. All right, so original equation here, we had x cubed plus y cubed equals 6xy. There's our fully moved Descartes. That's what it looks like. We were trying to find a tangent line through the point 3, 3. Okay, and what we got was y minus 3 equals -1 times x minus 3. If you look right here, the point 3, 3 is where that tangent line intersects that curve. Okay, so that checks out. That looks good. Again, that's just, it's a good way to check to make sure that you did your derivative correctly too, right? Because at this point, we know if we got the right tangent line, then our derivative must have been correct to give us the correct slope, okay? All right, so let's go back. Let's take a look at C now. So now we want to know at what point in the first quadrant would our tangent line be horizontal? How are we going to figure that out? All right, well, so let's start with this. If the tangent line is horizontal, what do we know? So what do we know about a horizontal tangent line? What do we know about a horizontal line in general? Okay, so it will, right? I agree with that. Think about what the derivative represents and think about what would be true about the derivative if the tangent line is horizontal. So first off, what does a derivative represent? So anytime you're finding a derivative, we're finding what? Slopes of tangent lines, right? So in this case, if we want that tangent line to be horizontal, what should its slope be? 0, right? So if we know the derivative represents the slopes of our tangent lines, and we need our tangent line to have a slope of 0 because it's horizontal, slope is 0, what could we do? So before we can do that, right, we don't have a point, right? That's what we're looking for, is that point. But we know the derivative represents the slope of a tangent line. We know what we want the slope of that tangent line to be. So what could we do? So here is our derivative that represents the slope of our tangent line. We know the slope of our tangent line is 0. So what are we going to do? Set it equal to 0. Exactly, right? We take the derivative now, which represents the slope of a tangent line. We need it to be equal to 0 to make it horizontal. So we're just going to set the derivative equal to 0 now. So this is just going to be 0 equals 6y minus 3x squared over 3y squared minus 6x. That's the type of question you're going to see over and over and over again about horizontal tangents. Just remember, horizontal lines have a slope of 0. You know the tangent line, the slope of it is represented by the derivative, so you're setting your derivative equal to 0 anytime those are the directions. Okay? Now, if this fraction is equal to 0, what actually needs to be equal to 0? The numerator, right? So I can kind of ignore the denominator and just say, well, this means that 0 equals 3y minus 3x, sorry, 6y minus 3x squared. Now, the only issue here is that we've got two different variables, right? So normally we would just have an x over there, we'd factor, we'd solve for x, no big deal. This time, though, we're going to have to do a little bit more work to think about what point this would represent. So here's how we're going to do it. I'm going to take this equation now. I'm going to solve it for y. So I'm going to move my 6y to the other side. We'll get negative 6y equals negative 3x squared. Then I'm just going to divide by the negative 6. So it's going to give us y equals 1/2 x squared. So now I know what y is equal to in terms of x. Now I can go back to my original equation at the top, and I can substitute 1/2 x squared everywhere I see a y, so that I can actually get a solution for my x value. Okay, so I'm going to go to a new slide here. So I've got room to work this out. So again, we're just taking the 1/2 x squared now, and we're substituting it into the original equation, okay, for both of these y's. Okay, so if we do that, we'll just copy the original equation real quick. X cubed plus y cubed was equal to 6xy. So that's going to give us x cubed plus, and in place of y now I'm putting 1/2 x squared. And that's going to be raised to the third equals 6 times x times y, which again is 1/2 x squared. And this will happen a lot with implicit because you're going to get derivatives that involve x's and y's a lot of times. You're going to have to find a way for specific points to get everything in terms of the same variable. Try to solve for 1 and then just plug that back into the original equation. That's how we're actually going to solve for x this time. All right, so now we just got to clean this up. So if we do this, we've got x cubed plus, if we cube this now, what's that going to give us? So what's 1/2 cubed? 1/8, good. And what is x squared cubed? Okay, so remember, when you raise a power to a power, we're actually going to do what with those exponents? X to the 6th, right? We multiply those together, so we're going to get x to the 6th power. Right, and then down here, we can just multiply this together. So 6 times 1/2, that's going to give us 3. And if we multiply the x's together, that's going to give us x to what power? X to the 3rd. Good. All right, now I'm just going to move everything to one side here so we can try to factor and solve for x. So subtract the 3x cubed, that's going to give us negative 2x cubed plus 1/8 x to the 6th equals 0. At that point, if you want to, we can get rid of the fraction. What would you have to multiply through by to get rid of that fraction? 8, right? So if I just multiply this entire equation now by 8, it's going to give us negative 16x cubed plus x to the 6th equals 0, right? So we're multiplying both sides by 8 here. Now what can we do to solve for x? Factor, right? It's a common factor here of x cubed. So if we factored that out, that's going to give us x cubed times negative 16 plus x cubed equals 0. Now we should be able to set each factor equal to 0. So we've got x cubed equals 0, negative 16 plus x cubed equals 0. So this first equation is going to give us x equals what? 0, right? And then the other one here, I'm just going to move my 16 over. So x cubed equals 16. And then we would have to do what? Good. Cube root. So that's just going to give us the cube root of 16, which is not an integer value, right? So if you just want to leave it that way, you could also bring out an 8 and get 2 cube root of 2, but cube root of 16 is fine there. Now, let me go back, because in this case, it told us that we wanted this to be in the first quadrant. Well, notice here, x equals 0, that's the y-axis, right? That's not going to be in the first quadrant because we need a positive x value. So we can ignore this one here because it's not where we want it. So the only x value we really care about is this x equals cube root of 16. Now it did want the point, okay, so now we need to find the actual y value that corresponds to that. But remember, we already said that y should be equal to 1/2 x squared. So the easiest way to find the y value is just to plug into that. So we're going to have y equals 1/2 times the cube root of 16 squared. Now, there are ways to simplify this if you really want to. Again, you could write that as 2 cube root of 2. Then you could square that, and then you could divide by the 2 and cancel it out. But honestly, if you get to this point, you could just say our point is the cube root of 16 and 1/2 cube root of 16 squared. Now, just so you know, right, something like this is not something I would give you on a test just because a test is timed, and I would rather see you doing other things that seem more productive. But there could be problems like this in the homework for sure. Okay, so make sure you're comfortable with the process. But this timely stuff, right, I'm usually not going to put on a test just because I know you're limited to 2 hours. Okay. Any questions about how we got there, though? All right, now let's look at the graph, right, because I do want to show you what we just found. So we have our original, right, that was the function here. We were looking for the point where we would have a horizontal tangent line. Well, if I graph this point now, cube root of 16 our x value, and then we had 1/2 of the cube root of 16. There's our point. And you can see those are the decimal approximations of those values. But you can see at that point, right, if you were to put a tangent line on that point now, it would indeed be horizontal, right? And if you really wanted to, you could find the actual equation of that line. In this case, though, it's just going to be y equals whatever the y value is. So 1/2 cube root. Let's see if I can just copy all of this. There you go. So there's our horizontal tangent that goes through that point there. Now, notice here, the other point that we got x equals 0, there would be a horizontal tangent at the origin also, but we wanted the point that was in the first quadrant. That's why we ignored the one that's at the origin here. Any questions on that one now? All right. Example 3. Okay, so again, we're just looking for y prime. This time we've got sine of x plus y equals y squared cosine x. So another example where we need to use implicit differentiation because we can't just solve this for y first. So let's start on the left-hand side. How are we going to find the derivative of our left-hand side here? So what rule do you think we might need to use to find the derivative on the left? It is a chain rule, right? Because we've got x plus y as our inside of the sine function. So I'm going to do a u substitution like I normally would, right? And I'm going to think about what this would look like. So if we rewrite this now as sine of u, where u is equal to x plus y, what would the derivative of sine give us? Just cosine u, right? So we're going to get cosine u, but because it's a chain rule, just don't forget we need u prime. So now I need to think about what's the derivative of x plus y going to give us. So what would that be? Remember, you can go term by term. So what's the derivative of x? Okay, so we're going to get 1 for the derivative of x. What's the derivative of y going to be, though? Because it's not just going to be 1. 1y prime, right? Because remember, we're taking the derivative now with respect to x, so that y has to have a y prime with it. Now we have our u and we have our u prime. Now we can substitute back in. So this derivative is going to be cosine of x plus y times 1 plus y prime. So that's the derivative of the left-hand side now. So we've got, I'll come down here and write it. So cosine x plus y times 1 plus y prime. Okay. Any questions about using the chain rule there to find the derivative of the left-hand side? All right, now let's look at the right-hand side. How are we going to find that derivative? Product, good. So in this case, we have y squared, we have cosine x. Those are our f and g functions, so that's how we're going to find that derivative. All right, so if we let f be y squared, let g be cosine x, what is f prime going to give us here? 2y, but because we're taking the derivative of y with respect to x, we also have to have what here? Y prime, good. And our g prime is going to give us what? Negative sine x. Perfect. And that's the derivative with respect to x, so we don't need anything additional to that one. Now we have all the pieces. Remember, product rule here is just going to give us fg prime plus gf prime. We've got y squared times negative sine of x plus cosine x times 2y y prime. Any questions up to that point about finding the derivative of either the left or the right-hand side? Okay, now we need to get y prime by itself. So what are we going to have to do first here if we're going to try to get y prime by itself? Okay, we do need to move them all to one side. Now, before we can do that, notice here on the left, we've got this cosine of x plus y times a sum of two things. So I'm actually going to have to distribute first before I can get all the y prime terms together. So if I do that, I'm distributing cosine of x plus y to the 1 and to the y prime here. So we're going to get cosine x plus y plus y prime cosine x plus y. And we have to do that because otherwise there's no way to get that y prime term with the other y prime term without moving stuff around. Okay, so you got to distribute first. Now we're going to get equals. Over here now I'm just going to move the negative. So negative y squared sine of x plus 2y y prime cosine of x. Now I have my terms where I can actually get all the y primes together, move everything else to the other side. So I'll just start by moving the cosine x plus y to the right. So we'll get y prime cosine x plus y equals negative y squared sine x plus 2y y prime cosine x minus cosine x plus y. And if you're good with moving multiple things in the same step, that's fine, right? If you can move the y prime and the cosine at the same time, feel free to do that. Now I'm going to move that y prime term from the right to the left. So we'll have y prime cosine x plus y minus 2y y prime cosine of x equals negative y squared sine of x minus cosine of x plus y. All right, now that we've got all the y primes together, now we can do what? Good, factor out the y prime. We have y prime, times cosine x plus y minus 2y cosine x. And then we have all this stuff over here that does not change. And so then our last step is to do what? Good. Go ahead and divide everything in those brackets. So y prime is going to be negative y squared sine of x minus cosine of x plus y all over cosine x plus y minus 2y cosine of x. And that is our final answer. Now, just so you know, if you had moved everything to the opposite sides, then obviously your signs would all be switched. And so in this case, if every one of these signs was opposite of what it is in the numerator and denominator, that's still equivalent, right? So if this had been positive y squared sine of x plus cosine x plus y, and we had a negative cosine of x plus y plus 2y cosine x in the denominator, that's the same answer that we just got here. So it doesn't matter which way you move your y primes, because in that case you could factor out a negative, cancel them out, right, and you'd have the same answer as what we've got here. Any questions on that example? And just so you know, the test will have a problem similar to this that involves some probably chain rule, maybe a product rule or quotient rule, probably product. I wouldn't give you quotient with implicit most likely, but also where you have some trig functions involved. Just to kind of, it's a good example to kind of combine a lot of different types of derivatives and things. Okay, so just keep in mind there will probably be a problem similar to this one on the test. right, example 4. So that's our last example in this section. This time we want to find y double prime, and our equation is x to the 4th plus y to the 4th equals 16. All right, so if we're looking for y double prime, what are we going to have to do first? You got to find y prime. Good. So to find the second derivative, we got to know the first derivative. So use implicit. If we go through each term here, x to the 4th, what's that derivative going to give us? Four x cubed. Good. So first term here, we get 4x cubed plus, what about the derivative of y to the 4th? Perfect. 4y cubed. And because we're taking the derivative with respect to x, we need a y prime there. And on the other side now, derivative of 16 is going to give us what? Just 0. Perfect. Now, in this case, we only have the one y prime term, so we can just solve for y prime from here. I'm going to move my 4x cubed to the other side. 4y cubed y prime equals negative 4x cubed. Now we can divide. So we get y prime equals negative 4x cubed over 4y cubed. 4's cancel out. And so our derivative this time is just negative x cubed over y cubed. Any questions on finding the first derivative here? Okay, now to find the second derivative, what are we going to have to do? It is a quotient. Good. There's nothing we can do to simplify this. You could technically move the y cubed up and make it a y to the negative 3, but then it just becomes a product rule, right? So it's kind of up to you which way you'd want to do it. Okay, but I'm just going to go with quotient rule here. So we'll let f be the numerator, negative x cubed. Let g be the denominator, y cubed. So what is our f prime going to be this time? Negative 3x squared. Good. And our g prime is going to give us what? Okay, 3y squared. But because it's implicit with respect to x, we actually have to have here a y prime also. Just don't forget that piece. And remember our quotient rule, we're going to start with g, so it's going to be gf prime minus fg prime all over g squared. So for our second derivative, we're going to get y cubed times negative 3x squared minus negative x cubed times 3y squared y prime all over g squared. That's y to the 3rd squared. Now, let's go ahead and simplify what we can in our numerator. So this is just going to give us a negative 3x squared y cubed for that first term. Double negative becomes a positive here. So this is plus 3x cubed y squared y prime all over. And in this case, we can go ahead and write that as y to the 6th. Right, that's easy enough to simplify. Now, we're not done. And the reason we're not done is because your second derivative needs to be in terms of x's and y's only. Right now, we have a y prime in our second derivative. So what are we going to have to do now? So if I want to get rid of that y prime, and I need all of this to be in terms of just x and y, what could I do? Yeah, we know what y prime is equal to, right? It's equal to this, and that's in terms of x and y. So we're just going to plug that in and get everything in terms of x and y now. So y double prime is going to be negative 3x squared y cubed plus 3x cubed y squared times negative x cubed over y cubed. All of that is over y to the sixth. Now, I'm going to stop there, right, because we are out of time. That answer is not completely simplified, okay, so I will show you tomorrow how we can do that. I don't want to rush it, though, because we wouldn't want to leave the fraction within a fraction, okay? So that's the only thing left at that point is to get rid of that piece. Otherwise, we're done, right? That's what the second derivative will be equal to. Okay, like I said, we'll start with that tomorrow, and then we'll get into section 2.8, which is our last section for the unit. Practice test has been posted, so if you want to start looking at that, feel free. But again, the main thing is don't forget the section 2.4 to 2.6 homework due by midnight tomorrow night. And that 2.8 homework, once we get into that section, that'll be due at the end of this week, along with the test, which will be posted midnight Wednesday night. Okay? Let me know if you've got any questions about anything. Again, feel free to stop in during student hours before class if you have any questions you need me to work through. Otherwise, have a great afternoon, and I will see you all tomorrow.